Hi. So good morning, everybody. I'm sorry I cannot, both show you my, face and my slides and the paper I'll use to do some computations. Thanks for being back. And today I will talk about mostly one-body properties of active systems, and in particular looking at the thermomechanical properties of active systems. So it may be a bit, may come as a surprising question that people have been interested by the pressure exerted by suspensions of bacteria or active particles. But actually, if you think a bit about where active matter comes from, and in particular its biological context, it starts to make a bit more sense. So on the top left here, you have an image of a single cell. And in green, what you can see is the actin cortex. At the bottom right of the picture, you see more redder part, which are called philopodia, which the cell is using to grab on a substrate, to pull on a substrate to move. Now, if you want to understand the motion of the cell, you have to be able to understand the statistics of the forces it's exerting on the substrate, and to get the mean force which is exerted, the fluctuations around it, and that means characterizing the statistics of the forces that the active medium, which is the actin cortex, is exerting on its surrounding. In the middle, you see two images at 12 hours difference, 10 hours difference, of a model wound healing experiment done in the lab of Pascal Silberzan in Paris. So the idea is that in the center, you have a monolayer of cells, which is confined between two regions, above and below, which they can't invade because of a mask. At t equals 0, you peel off the mask, and what you see on the right is that the cells start to invade collectively the free space. So there is an entropic component to this motion. Suddenly there is free space, so any random walk will make you invade the free space. But there is also a collective part of it, and this collective part of it is driven by the fact that cells push on each other. And then if you want to understand the motion of a tissue as an active fluid, you have to be able to write some kind of generalized Navier-Stokes, which means to understand what if you have a kind of stress tensor, and what are what is the physics of the forces exerted between the cells. And now on the top right, what you see is an experiment done in the lab of Roberto Di Leonardo. So if you put an asymmetric gear in an equilibrated bath, time reversal symmetry in steady state tells you that the gear cannot rotate. If you put it in a bath with bacteria, what you observe now is a steady rotation clockwise. To understand why you have this steady rotation and to characterize it, you would need to be able to do the statistics of the torques exerted by the bacterium on the gear, and that means understanding the forces. Now, if I tell you that each of these situations is super complicated and has a super rich physics, you will probably not be very surprised. What I would like to tell you today is that if you look at a much simpler situation, the most boring one you can think about, it is also full of surprise. And in particular, what I want to consider is an active fluid in a box at rest with nothing interesting happening, and I want to characterize its pressure. So you can play a game. When you go back to your labs, you can start asking your colleagues who are not in this talk, what is pressure? And what you'll see is that you get a whole bunch of different answers. If you have people who have, say, either a general physics background or engineering background, typically what they'll tell you is that mechanics is the force per unit area that the fluid exerts on its container. And that was pressure for me before I started working on that project. Then if in your lab there are people doing fluid dynamics, they'll give you a slightly different answer, which is that the pressure is minus the trace of the stress tensor divided by the number of spatial dimensions. And this is something which is already a bit more weird for most people, but the top of the answers is that statistical mech people will give you, which is that pressure is minus the derivative of the free energy with respect to volume. And then you've lost any connection to mechanics, and it's a very weird definition. Now, it turns out that in equilibrium, because of the Boltzmann weight, the statistical mechanics definition is equivalent to that of the mechanical pressure. And then mechanical pressure and harmonic pressure, they are typically given by momentum conservation. You divide a fluid in lots of small boxes. The boxes close to the wall exert the mechanical pressure on the wall, and it exerts a force on the next fluid element, which is the hydromic pressure. When you have an active system like cells crawling on a substrate, you're not in equilibrium. So the stat-mech pressure, not very useful, you don't have a free energy. But you don't have momentum conservation. When cells push on a substrate, they exchange momentum with the substrate. So you don't have momentum conservation, so the hydromic pressure, not very interesting. So the one we will look at today is the mechanical definition, which is also the simplest, which is simply the force exerted by an active fluid on its container. So I'm a theoretician. If I want to characterize this mechanical pressure, I have to find a setup in which I can compute it. To do that, the simplest setup I will start by considering is the one shown in the top left of the system. You have a box here in black with periodic boundary conditions in the vertical directions and confinements by a potential along the horizontal axis. So the system is invariant by translation, so everything interesting will happen along the x directions, and on the right you have a typical plot of what you expect. You have a density of particle in blue in the bulk, and when you get close to the confining wall, you have a repulsive potential that makes the density fall to zero, and there are no particles that are outside the bulk. If you want to compute the pressure in these 2D settings is the force per unit length exerted on the container. So you have to make a force density per unit length. If you take rho of xy, the density of particle, that's the density per unit area. Each particle experiences a force minus v prime from the potential, and so it exerts a force plus v prime on the wall. So the local force density is rho times v prime. If I integrate along x, I don't have a force density per unit area, I have a force density per unit length, and indeed if then I integrate what I've written here, P of y along y, I will get the total force. Just to show you that I haven't cheated, I can compute this for an ideal gas in equilibrium. So first I'd like to note that because the system is invariant by translation along y, P of y does not depend on y, and I can simply evaluate it at y equals 0. So imagine you have an ideal gas in equilibrium that you know that the density, rho, is simply rho naught times the Boltzmann weight, exponential minus v over kT. And here, because it's an ideal gas, I don't have any interactions. If I plug this expression into that of the pressure one line above, you see that exponential minus v times v prime is a total derivative. So I can do the integral explicitly. And what I get is simply the law of the ideal gas, P is rho kT. And I think that's the simplest demonstration you can find of the ideal gas law. Now, one thing which is very interesting in this expression is that if you look at the expression for the pressure written on the top, you see that VW appears in this expression. And so you could believe that because this integral seems to imply VW, the pressure will generically depend on the confining potential. But you know that's not true, because the pressure which is exerted by the gas in the room in which you are is the same on the walls, on your skin, maybe on the windows, and it does not depend on the property of the confining material. That's called satisfying an equation of state. And you can see it in P equal rho kT. The pressure is simply a function of numbers, the density, the temperature, which can be measured in the middle of the room and which are independent of the boundary condition. Now I have my setup. I have one important property of pressure in equilibrium systems, and I can try to compute the same number for active fluids. To do that, I have to define the active dynamics I will look at and to define the interactions between the active particles and the walls. So let's start with the dynamics I will consider. Again, I will look at the two same active dynamics as I considered on Monday. On the left, you have the run and tumble dynamics, which alternate runs in straight line with sudden reorientation of the particle. And that's a good model for bacterial motion. So here you have a movie of a bacterium which is arriving in one direction. So you see basically both the cell body and the flagella are stained fluorescently. Here you have a tumble during which the bacteria reorient, and you see that it's starting in a new direction. And on the top right, you have a schematic trajectory of what we call active radiant particles, in which again, you have self-propelled particles. So here, these guys are passive until I shed light on them. And when light is turned on, you see that they start to self-propel, and at this time, their orientation undergoes a continuous reorientation and not a complete randomization. Okay. So these will be by bulk dynamics. One thing that I want to specify is that in this talk, I focus only on the forces exerted by the active particles. So if you think about human beings walking in a room and pushing on the walls, the fact that they push on the ground to push on the walls is irrelevant if you're looking at the forces exerted on the walls. If you are swimming in a swimming pool, you're pushing on water to push on the wall, but water is also pushing on the wall. So if you wanted the total force exerted on the wall, you would have to consider both force exerted by active particles and by the solvent. What I'm trying to say is that if I consider active particles crawling on substrate, I don't need to consider the transmission of momentum from the substrate to the walls. If I was looking at swimmers, what I will be discussing in this talk is simply the osmotic pressure and not the pressure exerted by the fluid. Okay, so now I have my bulk dynamics, these radiant particles or these active radiant particles. They interact with a confining potential, and I have to say how they do that. So the first thing, which is pretty obvious, if you try to run towards a wall, is that the wall will not let you go through, and it will exert a repulsive force on you. Something which is maybe a bit less obvious is that if you're not a perfectly spherical frictionless particle, when you hit a wall, typically the wall will exert a torque on you. And that you can see by simply making a movie of bacteria colliding with a wall. So here on the left you have a wall, on the right you have a cavity. These rods are bacteria, and as you can see, most of them that you see swim along the wall, because when they collide with the wall, and at some point some guys will be arriving here, someone is arriving, there is basically a torque exerted on them, and they start swimming along the wall. So if you want to compute the pressure, you write the master equation for the probability of finding a particle at a given position going in the given direction. You take into account the repulsive forces, you take into account the torque exerted by the wall, and you can get an explicit expression for the pressure. The pressure is made of the sum of two terms. The first one in red, which I wrote P equal rho naught KTF, is simply the generalization of the ideal gas law to active particles. Again, you see that KTF is defined below. Gamma is the damping felt by the particles. V, their self-propulsion speed. dr, the rotational diffusivity. Alpha, the tumbling rate. KT would be the translational diffusivity divided by your mobility, if there is translational diffusion. And so you see that all these numbers can be measured in the bulk, and that do not depend on the confining potential. And so in a way, this would generalize a kind of equation of state part for the pressure. Now, if you look at the second term, which enters the pressure, you see that it's proportional to V, and it would be 0 in equilibrium, so that you would be back to P equal rho KT. And this guy involves the term in magenta, which is the torque exerted by the wall on a particle. And so what looks like is that generically, if you have a torque, then the pressure will depend on the type of the walls. And that means that the pressure is not solely a property of the fluid, but and so that there is no equation of state. So before I told you that there was magic which was happening in equilibrium, that I had VW prime in my definition for P here, but it was dropping out when I was making the computation. So you could think that here there is a torque which enters, but maybe magically it will cancel out when I will actually do the computation of these integrals. So let me show you that this is not the case. You consider self-propelled ellipsoids of principal axes A and B. So you can measure the anisotropy by A squared minus B squared. When kappa is 0, it's a circle. And you can find them in a harmonic wall, V of x, which is lambda x minus xw squared. So using the shape of the particles and the shape of the potential, you can compute explicitly the torque exerted on them. And it turns out that you can get a very good approximation for the steady-state distribution, which in the absence of translational diffusion is given here. You find that P is rho naught v square divided by 2 lambda kappa. Lambda is the stiffness of the potential, kappa is the anisotropy of the particle, times 1 minus exponential minus lambda kappa over dr. So here what's important is to know two things. If you send kappa to 0, you expand the exponential, the dependency on kappa and on lambda drops out, and you find that P is simply rho v square over 2 dr. So you're back with this rho KTF that I was talking about. If you look at the plot below, you have the pressure renormalized by the ideal gas law, so the term without the torque. And you see that when kappa lambda, which is the effective stiffness of the potential, goes to 0, you have indeed that P is given by rho KT. However, you see that when the particles are not isotropic, as you increase the stiffness of the potential, the pressure falls by a fraction which can be of order 1. Right? When the wall is very stiff, in this diffusion-free setting, you have a pressure that falls to 0. So can we understand that? Well, yes, imagine that you have a long and thin particle which arrives and collides with the wall. It's experiencing a reorienting torque. When the stiffness of the wall is very large, the reorientation time is very short, and the particle starts swimming along the wall. When it does so, it's essentially not transmitting its active force onto the wall, and the active contribution of the pressure falls to 0. That explains why you have no equation of state for generic active fluids, because spherical particles don't exist, frictionless particles don't exist. If you have a solvent, you'll get hydrodynamic interactions that give you a torque, and so generically, you will not get an equation of states. There are some exceptions. So, for instance, if you look at spherical particles without torques, you recover an equation of state, but these guys are exceptional. Now, one thing that you see on this cartoon is that the reason why the pressure drops is because the torque aligned the particle with the wall. You could imagine that instead of having long and thin bacteria, you have short and wide ones. Then the torque will be the opposite, and the bacteria would accumulate facing the wall, and you would expect that the torque leads to a larger force. Turns out you can also do the computation in this case, and it's plotted on this graph. And as you can see now, you have both the decaying pressure, which is the one that you find for long and thin particles, and the increasing pressure, which you find for short and wide bacteria. So the lack of equation of state is generic. The only case in which you have an equation of state is that of spherical particle, but you could wonder whether torques are the only way of breaking the equation of state. Why am I asking that? Well, if you look at the curve that you have in front of you, what you can see is that for roughly spherical particles, which means for weak torques, the equation of state is a very good approximation of the pressure you measure. So if you have an experimental system, you could wonder, well, maybe I'm close to this equation of state and maybe I shouldn't care about this torque. So clearly, one ingredient that real systems will have that these computations do not have is the role of interactions. So there are a bunch of interactions you can look at when you take active particles. On the top left here, you have a pressure versus the density when you have a hardcore repulsion between your particles. The straight line is the result you get for non-interacting particles. The symbols or simulations you obtain for the pressure of interacting particles, and the different colors correspond to different stiffness of the potential. And as you can see, all these points fall on the same master curve. So that I have, in this case, an equation of state for my interacting system of spherical particles, torque-free. And so in this case, hardcore repulsion does not break the existence of an equation of state. Now, another type of particle of interactions you can look at on the top right is what is called quorum sensing. Particles assume some form of energy which is stored in the environment to self-propel. So if there are a lot of you around me, you will have eaten most of the fuel and I will not be able to self-propel, so I will go slower. This is called the quorum sensing interaction, meaning that my self-propulsion statistics typically depend on people around me. Here you can see 3 different simulations with 3 different confining potentials with 3 different stiffnesses for the same interacting systems. And this time you see that the curves of the pressure versus the density do not fall on the master curve, so you don't have an equation of state. Another type of interactions that people have looked at, which is on the bottom right, is aligning interactions, like in a Witschek model or like for flock of birds. Again, you see that here, pressure versus density for different stiffnesses leads to different curves. So you have a rather confusing situation in which sometimes you add interactions and you preserve the equation of state. Sometimes you add interactions and you break down the equation of state. So these may seem a pretty confusing situations. It may also seem a pretty abstract consideration. You could think that at the end of the day, whether an equation of state exists or not is something that interests only stat-mech people and has no practical consequences. So let me show you a simple litmus test that you could do in principle in an experiment to test whether a system has or not an equation of state. Imagine that you take a cavity, which is homogeneously filled with a particle, and you place in the center an asymmetric mobile partition. So for instance, a wall that can move with a soft piece of gel on the left and a hard piece of metal on the right. Now, if you have an equation of state, like in the 2 situations depicted on the left, because the bulk properties of the fluid are the same in the left cavity and the right cavity, even though the wall in black in the center is asymmetric, very stiff on the right, very soft on the wall, the forces exerted on this wall from the left and from the right will be the same, and so the wall will simply fluctuate in the center. That will be true for non-interacting spherical ABPs or for ABPs interacting with WCA potential. On the right, here what you have is a case in which you have non-interacting elliptic ABPs, or ABPs interacting via quorum sensing, which you do not have an equation of state. Because you do not have an equation of state, if you have the same fluids on the 2 sides of the wall, because the wall is asymmetric, the force exerted on the right and on the left will be different, and you will get a spontaneous compression. So you can make a movie in which you turn, for instance, on and off the torque so that you go from the top left to the top right situation. You start with here wall which is asymmetric, so you can see the range of the potential in green and in blue are different, and you don't have a torque, and you see that the wall happily fluctuates in the center of the system. When you turn on the torque, suddenly the forces exerted on 2 sides of the walls are not the same anymore, and you have a spontaneous compression of the system, something that would be forbidden in equilibrium because clearly it's not maximizing entropy. So just to show you that this does not only happen in a computer, we built with Olivier Dochot a high-end experimental system, taking hex bugs and placing them in the Lego arena. And what you see in the center here is a mobile wall, which can move because of these wheels. And as the hex bugs collide with the wall, the letter will fluctuate. Sometimes it goes a bit to the right, sometimes it goes a bit to the left, but essentially it remains in the middle of the system. Now you go back to the lab, you work very hard, and you build a fancy asymmetric wall by simply gluing here a piece of foam on the left end of the mobile partition. And as you can see now, you have a very different type of collisions between the particles in the wall, and you have a spontaneous compression of the system to the right. Okay, now so far I've discussed in a way the simplest idealized situation in which I have a perfectly flat wall, I have periodic boundary conditions, and you could think that maybe this existence of equation of state is something that we work out only in these idealized situations, but as soon as you have rough walls or asymmetric ones, things will be more complicated. So what we want to do is to go away from these simple situations of an active fluid confined by a vertical flat wall. And the first thing that we can do is basically look at a torque-free active gas, but with a wall which is undulating. The first thing you can check is that there is still an equation for the mean force along X. So if I look at the force per unit area exerted on the boundary in the horizontal direction, it still satisfies an equation of states. However, a first difference with passive systems, which was noticed by Yeo and Philly some years ago, is that the pressure is non-uniform. Indeed, if the particles come from the left, it will typically spend a very small part along the concave perpendicular. It will slide along the wall and get stuck in the apices, so that you get high pressure points in some points and low pressure points in others. Now, from the point of view of these confining problems, it's not super interesting. But now, if you take a situation in which you have an active fluid on both sides of this partition, what is now a high pressure point from the left perspective is a low pressure point from the right perspective. So if this wall is not hard, but if it's flexible, this can drive an instability. And indeed, here you see a simulation in which you have a purely elastic line. So it's a bunch of particles connected by springs. And on the left and on the right, you have a dense gas of active particles that you don't see. At t equals 0, the flexible partition is flat. And as time goes on, you see that an instability develops. And that if you wait long enough, you basically get a coarsening. And at the end, you get a single period of this instability. And remember this shape because I will show you it in experiments in a minute. Now, this is what happens if basically you have a fully confining flexible partition, but you can play another role, another game, and you can imagine that instead of having an infinite confining partition, you have a finite flexible filament. What you can show is that if this flexible filament not only has an elasticity, but also a bending stiffness, then the Q equals 0 instability that happened previously becomes a finite wavelength instability. And this leads to a rich dynamics of flexible filament. So here, what I will show you are simulations of, yep, sorry, yes? Hello? Hello?
Hi, yeah, continue.
Yes. Okay, no question?
No.
Okay, sorry. So I have a gas of particles that you see in red here, which are interacting with flexible filaments in blue. The chain on the bottom left, 8, is smaller than half the period of the instability. 16, is below. Is a quarter of the period, 16 is half the period, 22 is above, and 30 is beyond. So as you run the dynamics, what you see is that the bottom left guy fluctuates and nothing happens. The bottom right guy is bent and has typically this parachute shape. Because it is asymmetric, now it acts as a ratchet. It will generate a current of particles, and it will be basically self-propelled in the other directions. And then if you look at the two filaments on the top, you see that you have sometimes parachute-shaped with self-propulsion. Sometimes you see a full period of the instability, and you start to see rotation, like right now on the bottom right. Sometimes you'll just see overfolding of the colloid. And so this interplay between active particles and flexible filaments leads to a very rich dynamics. So finally, before I make a short break concluding this first part, I want to speak about some experiments which has been done in the group of Olivier Dauchot. So what Olivier did is he considered an experimental system in which you have a bunch of self-propelled disks. So you put asymmetric disks on the plate, you vibrate the plate, and the disk move. And here on the left, you see an image seen from the top in which the active disks are confined by a flexible chain. So by looking at the radius of curvature of the chain and using Laplace law, you can measure the pressure exerted by this disk, and you can look at this pressure for two different stiffness of the chain. On the right, in blue, you find the pressure versus the packing fraction for symmetric equilibrium-like disks. And you see that when you use two different chains, you get either the disk or the squares, and you get measurements which are very close. When you take the active disk, however, you get two curves here which are very different. And so Olivier made a very nice experiments to distinguish these two cases. So do you see the movie now?
Yes.
Okay. So here what you have on the top are passive disks. And on the bottom, they are the self-propelled active disks. So what Olivier did was to compute the number of passive disks he has to put on the bottom to equilibrate the system. And the answer here is 200. So what you see is that these 200 rings lead to basically gentle horizontal fluctuation of this chain. Then at some point, he stopped vibrating the disks, he changed the chain, and he resumes the experiments. And what you see now is that the 200 disks at the bottom, they are able to compress the upper system, which means that the force they're exerting on this new chain is much larger. And if you can ask the question, how many disks should I have so that with this new chain, I get again a horizontal one? And the answer is 75. So you have to divide the density by 2 to get back to the same force. And this is basically what these red curves tells you, is that when you change chain, if you want to go back to the same pressure, you have to change density a lot. Finally, you can also play at the game in which you divide the cavity in two by a flexible partition, and you see this S shape, which is reminiscent of this instability I was talking about. Okay, so now I'll do a brief recap. Something we knew since the 90s is that out of equilibrium, you don't have a universal thermometer. If you measure temperature using kinetic energy or doing fluctuation dissipation, you will typically not get the same reading. Here, what I'm telling you is that there are no universal pressure gauge out of equilibrium. There are some exceptions which lead to equation of state. For instance, that's the case of spherical particles interacting with pairwise forces. In this case, the equation of state that we've computed is consistent with earlier approaches using the virial theorem, or virial formula. And nevertheless, even in these cases in which you have an equation of state, don't believe that everything is like in equilibrium. Even in these cases, you have a new physics. Now, I will now turn to discussing the physics behind this equation of state, because I think that everyone should be surprised that this momentum non-conserving system can have an equation of state. But before I do that, I'd like to know if you have some questions.
Yeah, there's one question.
Okay.
Yeah, so in the experiment, like, what was the difference between the two chains? I didn't get that.
So here it's the flexibility of the chain. So in one case you have a stiff chain, in the other one you have a flexible one. So it's like changing the stiffness of the potential if you want.
In the second case it was a more flexible chain.
Yes.
And what was the activity like? How did you make the active particles like?
So I didn't make them, it's Olivier Dochot who made them, but basically what he has, so you see it a bit better on the movies, maybe. So if you look at the disk on the bottom, you may see a small black dots on the disk.
Julien,
basically,
we can't see the movie.
You don't see my screen. Sorry. Okay. So here, if you look at the disk on the bottom, I don't know how good is the beamer, but you may be able to see a small black dots. So this disk, underneath them, they have two legs. They have a big one and a small one. So they're asymmetric. So if you put an asymmetric object on a plate and you vibrate the plate, the disk will start to move asymmetrically. On the top, what you have are isotropic disks. So when you vibrate the guys on the top, they have an equilibrium-like Brownian diffusion. And when you look at whether they have an equation of state, you get the blue curves, and basically the two measurements are very close to each other. But when you have the self-propelled ones, you see that they have a very different dynamics here on the bottom. I don't know if Olivier is coming to talk about his, or he's giving remote talks next week. Maybe I can have no, that's another problem. No, I don't have images of experiments. So it's basically asymmetric object that you vibrate. Are there any other questions, or do you want me to turn to the next part?
No, continue, please.
Oh, okay. So when we initially got these results, we found ourselves in a slightly frustrating situations. We were discussing with people, and either there were people with continuum mechanics background who tell us that, you know, pressure always has an equation of state, so your results are just wrong. Or we're talking with people from stat mech background who are telling us, but you know, you don't have a free energy. Why do you expect to have an equation of state? It's trivial. There shouldn't be an equation of state. So we were a bit annoyed of being either wrong or trivial, and we decided that we couldn't be both at the same time. And surely one of the cases must be interesting, either the case without interaction of state or the case with equation of state. And from our stat mech background, the idea that you don't have a momentum conserving system, you don't have a system in equilibrium, it should come as a surprise that an equation of state survives. So now during the next 6-7 slides, I will try to explain mathematically why there is an equation of state. I was planning to do that on the blackboard. It will be a bit harder on the slide, but I hope I can be pedagogical enough. So please, you can interrupt me with questions if there are things that you don't understand during the computation. Okay, so to discuss pressure and to discuss momentum conservation, the easiest way is to go back to underdamped system, so to system with inertia. So if you take an active particle with inertia and you look at its dynamics, what you will get is simply Hamilton's equation of motion. So you get that Ri dot is a velocity, and that mass times acceleration is the sum of forces. So typically you'll have damping, which I will here take linear. Then you may have external forces, minus grad Ri of V, and then Fi of u of theta I is the self-propulsion felt by particle I. So particle I is pushing on the substrate, exerting a force on the substrate minus Fi u of theta I, and so it feels from the substrate a force Fi u of theta I. And now I will consider the case of active Brownian particles, in which the direction of the particles is doing isotropic torque-free rotational diffusion. So that's the case in which I get an equation of state. Now, from these dynamics, I can build the dynamics of the momentum field. Okay, so each particle has a momentum mvi. So here in blue, I can define a field of momentum by summing over all the particles mvi delta of r minus ri, where delta is the Dirac function. And so you see that basically this is counting how much momentum there is in my system at position r. Okay, that's the density of momentum. Now I can compute the dynamics of this guy using my equation of motion. So if you look at P of r in blue, in this expression, there are two quantities which depends on time, vi and ri. So when I take the time derivative of P with respect to the time derivative of P, I will get a first term which is due to taking the derivative of mvi. So if you look on the top, mvi give you this magenta term, the three terms, minus gamma v, minus grad v, plus fi of u of theta. And consequently, in the equation I've written for dt p hat, you have the three magenta terms, minus gamma p hat, so the friction on the particle make the local momentum decay. Then the force on the particle minus grad v leads to a term minus rho grad v, which is a local force density. And then the self-propulsion force leads to the sum over I of Fi u of theta, delta of r minus Ri, which is the local density of active force. Then if you go back to the expression in blue of P hat of R, you see that you also have this delta of R minus Ri. When you take a derivative of Ri with respect to P, what you will get is minus Ri dot times the gradient of delta of R minus Ri. You can take the gradient out of this expression, and this leads to this term that you have in blue minus the divergence of J, where J is a momentum flux tensor. So J is sum over I of Vi, MVI, delta of R minus Ri, and VI is a tensor product. And this is very generic when you have a local field, so the sum of some observable times these delta functions. When you take the time derivative, you have the derivative of the observable that give you a local density, That's this term in magenta. And you have the derivative of the delta function, which give you a transport terms and minus the divergence of a flux. Okay. So now, if I look at the expression of the momentum, that's the dynamics of the momentum field. If I want to compute the pressure in the steady state, I can look at what this expression tells me in the steady state. So here I'm just going back to my setup in which I have my box, my confining potentials, my periodic boundary conditions along the vertical directions, and I go in steady state. Now, because I have a system invariant by translation along y, I cannot have any net flow along y in the steady state, and I will have a zero momentum flux along y. So the only momentum flux I could have is along x. But because I have confining boundaries, I will not have confining boundary. So if I go into the steady state, I get a flux-free steady state, and the mean local momentum field is 0. Forget about the lambda. That was just because I was first doing the case with translational diffusion, and I forget to remove it. So if I look at the dynamics for the momentum field in steady state, what I have is simply that dtpx is equal to 0. And if I look at what this guy is equal to, it will be minus rho, which would be dxv, not grad v. So that's the local force density, plus the term in magenta, which is the local density of active force along the x direction, minus the divergence of my momentum flux tensor, which is just minus dx of jxx. So now I can take the rho grad v and put it on the other side of the equal sign, and I get that the local density of external force is given by the sum between the magenta and the blue terms. So if I want to compute the pressure, what I have to compute is the integral from 0 to infinity of rho dxv. But now, if I look at the contribution because of the flux of momentum, dx of jax, if I integrate dx of something, I just get jxx evaluated at 0 minus jxx at plus infinity. There are no particles outside the box, so jxx will be 0. There is no momentum flux at infinity. And so the pressure is equal to just jxx at 0 in the center of the box plus the term in magenta, which is the integral from 0 to infinity of the local density of active force. Now, if you look at the cartoon, the picture on the top left, what this is saying is super simple. You're looking at the force exerted on the right wall, okay? And what you're just saying is that if I look at just mechanical balance, the force exerted on the right wall is basically the momentum flux entering the right half of the system plus the local force density. Why? Because you have a momentum flux that enters the system at j equals 0, at x equals 0. It will fall to 0 outside the system. The only way the momentum flux can change is by exerting forces. The only two types of forces which are exerted are the active force and the force exerted by the wall. And so you know that the fall down of jxx from its value in the bulk to 0 are due to the two forces. If you rewrite that as the pressure, so the force in the right half of the wall, you find that it's equal to the flux of the momentum entering the right half of the system plus the active force exerted on the right half of the system. And now here, you can see why you should be surprised that an equation of state exists. If you have a passive system, you don't have any active force, and you find that mechanical pressure is just momentum flux in the bulk. That's the standard equation of state. Now you see that the contribution of activity is to add the total active force exerted on the right half of the system. And that includes the active force density exerted close to the wall. But now imagine that I take different confining wall, right? So I take, for instance, a harmonic confining wall. Vx is minus lambda times x minus x whole square. And I look at three different wall stiffnesses. What you see on the left is, because I have different potentials, I have different density of active particles, which makes perfect sense. But the result of that is that I will also have different density of active force. So if I have different density of active force, how can there be an equation of state? And the answer to that is because there is a hidden conservation law that I will not present, which is the hidden conservation law of what I call the active impulse, which is a quantity I want to introduce now. So let's go back to our microscopic model. We have our active Brownian particles. The mass time acceleration is minus the damping plus the active force minus the external potential. And the dynamics of the angle is simply a random walk. Now, we want to understand the density of active force exerted by these particles. So we want to look at, in a way, the average force exerted by particles. And now suddenly there's something a bit surprising. If you look at the dynamics on theta, what you find is that, well, on average, because theta is just doing a random walk, the average of Fi u of theta is 0. So if I just follow a particle through time, on average, the force it experiences from the substrate, if it's doing a random walk, is 0, because it's the average of an isotropic number. However, the momentum gain between now and the end of time is something which will not be 0. Imagine that you take the active particle, which is on the right here, which is pointing slightly rightwards, upwards. If I compute the integral between now and the end of time of its active force, we know that in 10 seconds from now, this particle will have forgotten its initial direction. But for some time, it will keep going in these upright directions so that the mean momentum gain it will receive from the substrate is non-zero. I can actually compute that for ABPs. That's what you do. That's what I did on the bottom line. And for ABPs, if I compute the mean change of momentum due to the active force, which is the integral of the active force between now and the end of time, what I find is simply Fi over dr times u of theta. So for a class of what I would call stub-born active particles, which are particles whose active force is independent of any other degree of freedom, the mean momentum they receive from the substrate is independent from the rest of the world, and in particular, it's independent from the confining potential. So if you look at the dynamics of an ABP on the top, Fi is a constant. Theta I is doing an isotropic random walk independent of the potential. There is no torque. So the mean momentum it receives between now and the end of time from the substrate is independent of the confining potential. Because the pressure is just a transfer of momentum, the stock of momentum a particle has to transfer on a wall does not depend on the wall. This can be explained a bit more mathematically by realizing that the active pulse really mathematically is a stock of momentum which is to be transferred. How do you notice that? You look at the expression of this active impulse, delta pi A active, and you take its derivative with respect to time. So the other bar here is an average over trajectories in the future. So if I take a derivative of this expression, I just get the integrand evaluated at the lower limit. So I find that dt of delta pi A is minus my active force. So the way that my active impulse varies through time is by exerting an active force. Now I can define an active impulse field by summing over the particles, the active impulse of the particles, and localizing it with a delta function. I can compute the dynamics of this field, and as before, I will have one term that comes from the evolution of the observable, and the divergence of a flux that comes from the delta function. So the dynamics of PA, of delta PA, is given in red on the top, and it tells me that dt of delta pi A is minus the active force. So this will lead to the first term in the right-hand side of the equation of the bottom. The time variation of the active force field locally is minus the force density exerted locally. And then there is a second term on the right, which is minus the divergence of the flux. There is a VI. A flux of what? A flux of active impulse. Again, if I go in steady state, dt of delta pi A will be 0. And what I get is that the local density of active force is minus the divergence of the flux of active impulse. And this gives me an effective conservation law. If I go back to the pressure was the flux of momentum in the bulk of the system plus the integral of the density of active force. But the density of active force is minus the divergence of the flux of active impulse. So I have the integral of a divergence, which gives me again boundary terms. And what you see at the bottom is that the pressure becomes the sum of the momentum flux at x equals 0 plus the active impulse at x equals 0. Again, if we go back to our initial system, the idea is that on the right-hand side of the system, because on average the particles don't exert any force, the only force they can exert is the one they brought in when they crossed the blue line. And what you find is that the pressure exerted on the right boundary of the system is the flux of the momentum they carried with them when they enter the right-hand side and the active impulse. If you want to understand what this is meaning, think about yourself trying to catch a small kid running toward you. Okay, you're the wall. The kid is running toward you. The pressure is the momentum the kids will transfer to you when it will bump into you. So to slow down the kids, you have to take its momentum and bring it to 0. But you know what happens when you do that? Kids are stubborn. So when you have stopped them and brought their speed to 0, the kids will keep running and they will keep pushing into you. That's the active impulse that you also have to absorb. And then after some time, they get bored and they go elsewhere and they've transmitted all the momentum. So the take-home message from this part is that when the dynamics of the active force is independent of other degrees of freedom, the active impulse becomes independent of the confining potential, and that gives you an equation of state. The wall has to absorb both the momentum and the active impulse of the particles. So when you don't have an equation, an external force, you get just that 0 is minus divergence of J plus G, which is this effective conservation law that I was talking about. And the equation of state tells you that Jxx plus Gxx has to go from its bulk value to 0 outside the system. Different walls will tell you that the way these flux fall from the bulk value to 0 will be potential dependent, but the height of the fall is independent. Okay, to explain to you results I got for overdamped active matter, I used an underdamped model, which is something a bit weird, and most systems are not underdamped, they're overdamped, so you may wonder what changes if I go into the overdamped limit. So what you can do is you can take these underdamped dynamics of active Brownian particles and look at the overdamped limit. So you can plot both the active impulse flux and the momentum flux as function of the mass. And you find that both of them depends on the mass. However, if you compute their sum, which is the pressure, you find that it doesn't. So here on its graph, what you have in blue, which is constant, is the pressure as function of the mass, which is the sum of, in green, the flux of active impulse, and in red, the momentum flux. Overdamped active matter is the limit m goes to 0. The flux in this case of momentum falls to 0 because essentially momentum falls to 0, and the pressure in this case is simply given by the active impulse. So that's what you find in most active matter paper that speaks about equation of state. The pressure is a sum between a passive pressure, rho kt, maybe some Irving-Kirkwood tensor if you have pairwise interactions, plus an active pressure, and this active pressure is nothing but the flux of active impulse. Okay, you can look at cases in which you don't have an equation of state. You can look at the difference between the active force density and the flux of the divergence of the flux of active impulse. And here what you have is this difference between these momentum conserving bits and these momentum sources. When you have 3 different confining potentials on the right, you basically get 3 different types of momentum sources. And on the bottom left, what you have is in blue, the flux of momentum, in green, the flux of active impulse versus the stiffness of the potential. These are constants. In red, you have the momentum source, which are due to the torques and which will depend on the confining potential. And you find that this dependency on the potential completely account for the dependency of the total pressure with the stiffness of the potential. Now, I conclude this more technical part. I hope that you're not all dead. The take-home message of this complete first part on pressure is that mechanical pressure is a subtle concept in active systems. Generically, you don't have any equation of state. The active force, if the active force is independent of other degree of freedom, you get an effective conservation law, and that leads to the emergence of equation of states. Now, in the last 10 or so minutes of my talks, what I want to talk about is not bulk pressure, but surface tension. So if I've killed you with computations, it's a good time to wake up again. The reason why surface tension is interesting, and I would say even more interesting than pressure, is that interfaces are ubiquitous in active matter. You have them everywhere, whether close to confining systems or between phases. And we know essentially nothing about their mechanical properties. So if you have some questions, I can answer them now, or I can move on to surface tension, as you wish.
Hello?
Yes?
Yeah, please continue.
Okay. So, surface tension. In equilibrium, if you open any paper on surface tension, the definition of surface tension is made by looking at change of the free energy when you deform a system, preserving the volume. So in 3D, you take this cube that you have on top left and you make it into these parallelepiped shapes, which has the same volume but not the same area. And gamma is then basically the variation of the free energy due to the change of area at fixed volume. In 2D, it's a bit simpler. You go from a square to a rectangle. So you make a change of the system, preserving the area but changing the perimeter. And gamma is simply the variation of the free energy with the perimeter. If you go back to my favorite setting, in which I have this 2D system in which my walls are modeled by repulsive potentials, you can compute, using this derivative of the free energy with respect to the perimeter formula, you can compute the ideal gas, the surface tension between the ideal gas and the confining walls. So it's a solid fluid surface tension. And the expression you find is minus kT times the integral between the beginning of the wall and infinity of the density. So you essentially look at the mass of the system which is in the contact with the wall, and you compute rho kT. You sum up the rho kT. Now, that's something that you can do for an equilibrium system. But for a non-equilibrium system, again, you have the problem that we don't have free energies. So using these free energy definitions is very difficult. And the way to do that is instead, again, to revert to mechanics. Okay. So let me introduce a setup that can be used in equilibrium to compute the surface tension in equilibrium fluid. So imagine that you have, so it's called the Langmuir gauge. It was introduced almost a century ago by Langmuir. You take a box in which you have a fluid, and on top of it, you put a wall, which is mobile, which is made up of two materials. You have material 1 and material 2, and both of them are in contact with a fluid. Now, this upper confining boundary is mobile, and it can move, and when it moves, it exerts a force Fx on the spring. Okay? If this wall moves horizontally, you see that the lengths L1 and L2 of contact between material 1 and the fluid and material 2 in the fluid will change. And because these lengths are related to the surface tension, that will exert a force. There is a force exerted by the fluid on the material. You can compute this force by saying that the free energy of the fluid is basically a bulk free energy proportional to the volume, plus gamma 1 L1, where gamma 1 is the surface tension between the fluid and material 1, plus gamma 2 L2, which is gamma 2 L minus L1, plus a contribution of the free energy, which is due to the junction. If I compute the free energy derivative, so if I want to compute the force, the generalized forces exerted by the fluid on the upper boundary, I simply have to take minus the derivative of the free energy with respect to gamma 1, to L1, sorry. So Fx is minus dF over dL1. And if you read the formula, what you get is simply gamma 2 minus gamma 1. This is just saying that if I move a little bit my wall leftward or rightward, the interaction between the fluid and the junction doesn't change. The bulk free energy of the system doesn't change. The only thing I've changed are the lengths of contact between material 1 and fluid, material 2 and fluid. These are related to the surface tension. If material 2 is pulling stronger on the fluid, essentially what will happen is that the system will move to the right. If it's material 1, the system will move to the left, and that's why Fx is simply gamma 2 minus gamma 1. So one thing that you can see again is that, like for the pressure, in a way there is a kind of equation of state statement, which is that this force here, it's independent of the details of the junction. So whether you've glued with a piece of metal or with a glue or with a piece of gel, these two materials, whatever the junction you've used, the force that will be exerted by the fluid on this upper boundary is independent of the details on the junction. So let's check whether this is true. Imagine you take Brownian particles, okay, and you make a simulation in which you have your Brownian particles which are in this box, and they are confined by this upper system. So what do? Well, I have equilibrium Brownian dynamics for my colloids. My upper wall V of xy is now a potential which is not invariant by translation along x, okay? I typically have confinement in the y direction, which is given by lambda times 1 minus yw to the power 4. So the confinement happens only when y is larger than yw. But the stiffness of material 1 is lambda 1, the stiffness of material 2 is lambda 2, and they are not the same. And so I have to interpolate between these two materials, and that's what I do on the bottom right with basically a hyperbolic tangent. So this stiffness lambda of x, when I'm on the left of the junction, it's lambda 1, on the right of the junction, it's lambda 2, and I have a small region of width w in which my potential interpolates between the stiffness 1 and stiffness 2. To check the existence of this equation of state, what I can do is I can measure the total force exerted by the fluid on the junction in a big box that comprises the junction. If I do that and I change the width of my potential, I can check two things. First, that the force I measure, which is given by the blue crosses, is indeed independent of the width of the junction. So however I glue my two materials, the force exerted on the upper wall is the same. The second thing is I can actually compute my predictions, which was that Fx was gamma 2 minus gamma 1, and that gamma was the expression I had from my free energy computations. And if I do that, I predict the horizontal magenta line, and indeed you see that the simulations fit perfectly with the measurement. And now I'm very happy because this guy is a setup I can use for passive particles, but I can also use for active particles. So I can do exactly the same thing using active Brownian dynamics. So I have R dot is the self-propulsion bit minus the gradient of my external potential, and the dynamics of my active force is theta dot equal root 2 dr. So remember that here, these were IBPs, and so these are the system for which my pressure has an equation of state. So in a way, I'm in the case in which I expect results to be gentle, like in equilibrium. So again, I can measure the force, and I can measure the force versus the width of my junction. And now what you find is that even though this is a system whose pressure will have an equation of state, you see that the tangential forces exerted on the wall now depends on the junction width, so that I do not have an equation of state for Fx. Okay, and essentially what I want to tell you in the following is why and what is the physics. So who's the culprit? Who's breaking down our equation of states? Look at the dynamics of your system. It's super simple, right? You have the speed, the velocity, which is given by self-propulsion speed plus external force. Not much is happening. And I want to compute the force along the x direction exerted in this blue box, which I've drawn here. So I introduced the local density of particles, rho of r, which is the sum over I of delta of r minus ri, which simply counts the density of particles at position r, and I compute its dynamics by taking the derivative of this guy. Why is this a useful quantity? Well, if you look at the expression of Fw written on the right, you see that Fw is simply the sum of all particles in this box of dxv of xi yi, and this I can simply write it as the integral in this whole box of the density of particles times dx times v. So if I can compute rho, I can compute Fw. To compute rho, I write down its dynamics. Rho dot is the sum of delta of r minus ri. Only ri depends on time. When I take the time derivative of rho, I will get that rho dot is minus the divergence of j, where j is simply sum over I of ri dot delta of r minus ri. I can replace ri dot by its expression, and I get that my current is the sum of two terms. One term in red is the contribution to the current of the self-propulsion, J active. It's simply sum over I of V naught U of theta I, delta R minus Ri. And then in blue, you have a contribution to the current due to the external force, which is minus mu rho grad V. So then I want to compute F, which is the integral of rho grad V. I can simply use the fact that J act minus mu rho grad V, and I simply write that the force is 1 over mu, the integral over this area of J active, the X component of J active minus the X component of the current. Okay. So if I know how to compute this guy in steady state, I'm good. Now, if you remember the previous part of my talk, J active, that's simply the mobility times the density of the active force, and the density of the active force is simply the divergence of the flux of active impulse. So when I compute the integral over an area of the divergence of my active flux of active impulse, what I will get is simply the flux of the active impulse through the boundaries using Stokes' theorem. The upper boundary and the lower boundary will not give any contribution because Jxy will be 0. And the only contribution I will have is basically the flux of active impulse through the left boundary minus the flux of active impulse through the right boundary. So I will look now at the expression of the force as this difference between the fluxes of active impulse on the left and the right minus this 1 over mu times the integral over the area of the current. So I take my volume, and the first contribution to the force is the difference between the flux of active impulse that comes in from the left and the one that leaves out from the right. Okay? If I compute explicitly the expression of Jxx that was in this expression, I get something that looks a lot like the surface tension defined in equilibrium. Instead of having the integral of rho kt, I get essentially the integral of rho v square over 2dr, which is just the generalization of the momentum transfer to active particles. And this first contribution to the tangential force would be an equation of state abiding part. You see that here in this Fw equal gamma 2 minus gamma 1, where gamma 2 and gamma 1 are just the flux of active impulse through my two boundaries. I'm far away from the junction that would give me contributions which do not depend on the junction. So where does the dependence on the junction comes from? It comes from the second term. Fw also has a contribution which is minus 1 over mu, the integral over this area of the current. Now, this current, you have a system which is left-right asymmetric. It's out of equilibrium. These act as a ratchet, and generically, you will indeed get a current. If you look at the expression of the current, why it happens there is super simple. J is simply the sum of I of Ri dot delta of R minus Ri. So when I look at the integral of the current over the whole box, what I get is the drag force. So this expression in blue, that Fw is gamma 2 minus gamma 1 plus Fd, is equivalent to saying that the difference of active impulse between what comes in on the left and what comes out on the right is what has been spent to produce a force in between. It has been produced to produce a force on the wall and a dissipation on the substrate. And so again, this is just mechanical balance. The force exerted on the junction is the momentum stock which has been spent minus the part which has been spent to produce a drag force. So now, do this current really exist? As I told you, close to the junction, we have, say, a soft wall on the left, a hard wall on the right. We can go in the steady state and measure the flux of particle. And what we find is that we indeed have a flow which is of a dipolar nature. And this is something which has been looked at quite some time in the past by Satya Majumdar and David Mukamel, who had looked at a system of spin in which locally you are driving one bond between two spins out of equilibrium. That would typically generate a dipolar flow. Well, here the same thing is happening. Close to my junction, I have a local asymmetry between the soft wall and the hard wall. This generates a dipolar current. This dipolar current will generate a drag force. This drag force will be junction dependent, and this will lead to a junction dependent component contribution to the force. You can check that. Here what you have on the top right is in the drag force in black, which is the top curve, which as you see depends on the width of the junction. Then you have delta gamma, the difference of surface tension between the left wall and the fluid and the right wall and the fluid, measured far away from the junction, which indeed does not depend on the junction. And you see that their sum in red completely accounts for the measure of the tangential force in blue, and completely account in particular for the dependency on the junction. So even when you have a system which has an equation of state, the left-right asymmetry of the system generates ratchet currents, which generates a non-zero steady drag that consume part of the active impulse you have and lead to forces which are dependent on the structure of the junction. If I wanted to speak in a kind of fancy way, I would say that the bare equation of state for the surface tension, which exists, which is this gamma 2 minus gamma 1, which for instance would play a role if you were to compute the Laplace pressure of a system, is in this setup dressed by the current generated by the junction, so that the tangential forces are not given by the equation of state. With that, I will conclude my talk. I want to thank you for your attention and all my collaborators. For the pressure, Aparna Bhaskaran, Mike Cates, Yawen Philly, Yariv Kafri, with whom I started this whole work, Mehran Kardar, Alex Solon, who was a very talented PhD student who did most of this work, and Harry Turner. And for the surface tension work, Adrian Daher, who suggested us the setup that we looked at, Yariv Kafri, Milos Nezevic, Ruben Zakin, and Yangfeng Zhao, who are the three young guys that did all the work, and Fred van Wijland, with whom I've worked on surface tension for all these years. And with that, I thank you for your attentions, and I'm happy to take questions if you have any.
Julien.